Let's restate the goal of this entire book, because it's easy to lose sight of it under this notation. So what we want to do is we want some approximation, f hat, to some true underlying function, f. But the problem is we don't observe f directly. All we have is the inputs and outputs. Now, we've already found two ways to get at this. Back in week 23, we showed that under squared error loss, the best possible function to aim for is the regression function itself. So this was the regression function that we're trying to approximate under L2 or squared error loss. And back in week 22, we saw that the k nearest neighbors is really trying to approximate that same conditional expectation, just locally and with a finite number of points. Yeah, so we saw last time that our k nearest neighbors evaluation was from just taking the average around our point of interest, x, in some neighborhood around x, and then divided by the number of points in the neighborhood. And so this is a direct, local, and finite approximation of this expected value expression. And as we saw last week with the cursive dimensionality, it fails in two specific ways as we increase our dimensions. So if the dimension of the input space is high, nearest neighbors don't actually end up close to the target point anymore. We spent all last week exactly on this problem. And if we already know something about the structure of the true relationship, for example, if the true relationship was linear, we're sort of leaving that knowledge on the table by not using it. And using it could reduce both bias and variance. Now, of course, because k nearest neighbors is completely unstructured, it cannot simply survive high dimensions. And that's the whole reason the rest of the book exists. It's about inventing other classes of models, like linear models, decision trees, support vector machines, and neural networks, and still, all still to come. But every single one of them does the same fundamental thing. It imposes a mathematical assumptions or this, structure onto the data, specifically to bypass the cursive dimensionality we talked about last week. So recall, this is the bias variance decomposition, where we have some irreducible noise in our system. We cannot predict it because it truly is random. And then we have the bias, which is how far away our model is from predicting the true value. And we have the variance of our model, which is, given sampling many times, how much can we expect our prediction might change. So what we're doing when we impose structure onto our data is that we're intentionally increasing potentially bias, but we're decreasing variance. That's what we're kind of doing, generally speaking. Here's another way to picture it. Without structure, the space of functions you're searching over is enormous. Genuinely, every possible function is candidate. The moment you impose an assumption, say like linear, then you collapse that enormous search space down into something tiny and intractable. So you give up some correctness for a massive reduction on how much data you actually need to make that prediction. So here's a schema of what I mean. The space of all possible functions is huge, but as soon as you collapse it or you impose some structure, that search space greatly collapses, and you only need to search in this space. Okay, so we've motivated why we need a structure. Now let's actually build a statistical model that's underneath it all. We believe that the true underlying world is based on a deterministic signal plus a random noise. And when we sample or gather our data set, we're sampling from this distribution here. So we're getting yi, yi plus 1, etc., etc. And we also tend to make an assumption that the expected value or the average error is 0. So looking at this graph here, here's what we mean. So the true function f is this blue deterministic line. And then, we're sort of adding these random errors here. And, these are our y values. So, of course, this is the story for regression. And in fact, this looks like linear regression. But when we say regression problems in general, we really mean this underlying structure. On the other hand, classification asks something different. Instead of modeling value additively, we model the probability directly. So notice in classification, we don't model y with respect to some function of x and some error term. We model the distributions themselves. Now, why is this true? It's true because the way probability works, the variance of y given x, so y given x, is not a free parameter anymore. It's sort of locked to the mean. So specifically for a binary outcome, we have the following. So what this is telling you is that the mean, which in this case, since it's binary, is simply the probability of x, is tied to this variance by this equation. So think about what this means in two concrete cases. If the probability p of x is 0.99, we're almost certain the email is spam. The variance is also tiny. So because our expected value is high, our variance is low. If our probability is 0.5, then the variance is huge. In fact, is maximum at probability of 0.5. So the variance and the expected value are related to each other. Again, that's not true for the regression problems. Those are separate. So this gives us a deep distinction between regression and classification. And I don't think this gets said enough. In regression, predicting a value tells you nothing about the noisy environments, f of x and epsilon. Those are independent by construction. But in classification, the prediction is the noise. You literally cannot separate them. Think about trying to add noise to a category, the way that you would add it to any other number. Like if you're trying to predict a spam, so y is spam, and you have the true number plus some noise. Spam is the true number plus noise. Well, that doesn't make any sense because y must be 0 or 1, either spam or not spam. It can't be some decimal. So the only place uncertainty can live is inside the probability itself. So regression, the noise and the true values are independent. However, in classification, they're intimately connected together. The prediction is both a prediction and a comment or information about its uncertainty. Great. So now that we have a statistical model for the data, let's formalize what we actually mean by learning in machine learning. So supervised learning is learning F by example through what the book calls, a teacher. We observe a system under study, both its inputs and its outputs, and we collect these into some training set. So we have n pairs of points. X is our observation and Y is our response. And we simply observe the training set. So then these points are fed into the learning algorithm. And here's the defining property of that algorithm. It's able to modify its own input-output relationship, f hat, in response to the difference between what is predicted and what's actually true in our training set. So our function is updated using the difference between the true value in our training set, these y's here, against its own predicted value, which is itself. So here's a simple diagram, a way you can think about machine learning models. We start simply by observing our training data, and then we find some model, f hat. And then we ask, how good is our model, f hat? And so it makes a prediction, and then we compare the prediction to yi. And then based on that difference, we can then adjust our model and continue in that loop until we're satisfied with our model. The approach taken by this book, and by applied statistics generally speaking, is to treat this problem as a problem in what's called function approximation in estimation. So, consider each data point, xi and yi. It's just a point sitting in p+1 dimensional space. Why is it p+1? It's because this is in R of p space, and this is R of 1 space, meaning each observation is a vector of numbers, and the resulting value of interest that we're trying to predict is simply just one number. Okay, and our goal is to find a useful approximation to f across some region in R of p, given a finite sample training set. Okay, so now up until this point, all the way back through week 22, we've justified using least squares because it made a sort of intuitive geometric sense, minimizing the distance between predictions and reality. Now that's a perfectly good reason, but it's about to be replaced by something much deeper. And that something much deeper is the broader statistical philosophy called maximum likelihood estimation, or MLE. So instead of asking a geometric question, it asks a probabilistic one. Given the exact data set we just observed, our training data set, which model parameters make the specific training data set most probable? So to answer that, you'd have to figure out the probability of each individual data point occurring under your model. Then you multiply them all together to get your total probability of that particular data set. And then you find the parameters that maximize that number. So let's walk through an example. Let's assume for now that our outputs are continuous and the noise are Gaussian. So the probability of response y given our data, x, and our model parameters, theta, is given by this expression here. This is just the PDF or probability density function of the Gaussian data. Now notice that our only assumption is that our error terms, epsilon, is distributed as normal, with mean 0 and some variance sigma squared. This is the only assumption, and so we can write out the PDF of the normal distribution as follows. Now, this is the probability of observing a single point, but we want the probability of our entire data set. So we want to multiply this probability by all the other probabilities of each other point. Now, I'll do one more step in that as well, which is we want to take the log of that probability as follows. Now, because we've taken the log here, the multiplication terms goes to the summation term. So this is called often the log likelihood, because we're literally taking the log of the likelihood, where again, the likelihood is the probability of observing our data set. And of course, we can expand this term out as follows. I know that this term does not depend on the summation, so we can pull that out with the n multiplied here, and we have this. Now, since this term is constant with respect to theta, or our parameters, maximizing this log likelihood is equivalent to maximizing the second term alone. And because this negative 1/2 sigma squared is simply just a constant, right? This is given here, this is a constant. We know that to maximize this entire term, is the equivalent of just minimizing this term here. Now, hopefully that looks familiar, and hopefully your mind, if you haven't seen this before, is blown. Because, look at this new expression here. That's not a new formula. That's the residual sum of squares we saw earlier in everywhere in machine learning. This is the exact object we spent all of week 22 minimizing. Except now we understand something we didn't back in week 22, which is that residual sum of squares was never just a natural geometric choice. It's literally the maximum likelihood estimate under the specific assumption that your noise follows a Gaussian distribution. So looking at this diagram, we saw again that the residual sum of squares over our parameters, in the case of linear regression, we have these beta 1 and beta 2, is equivalent to assuming that our noise is Gaussian. So why did I claim earlier that maximum likelihood estimate is a more powerful framework than just this intuitive geometric interpretation on the left-hand side? Well, the reason is that this Gaussian assumption here, we don't have to choose, we don't have to assume this is true. We can assume something else is true about these error terms. So let's do exactly that. Let's make a different assumption and let's see what we get. But before we do that, let's set up the general procedure for how we do that. So in general, assuming that the pair xi and yi are independent, the total likelihood of the dataset is simply the product of the individual probabilities, right? It's just the product of the individual probabilities, and that gives us our likelihood. Now, we like to work at log likelihood, so taking the log, we saw earlier that we have the following here, which is what's called a negative log likelihood, where we have a negative and we simply take the log, and so this product goes into a summation. So this is sort of the machine I want to hold onto. Pick a distribution for this term here. Last time we assumed that this distribution was Gaussian. Now let's see what we do. What happens if we pick a different distribution. So say we're still predicting continuous values, but we think our noise has what's called fat tails. Maybe outliers are common. So Gaussian noise punishes big errors quadratically, which we think is now too harsh if large errors are expected to happen sometimes. So instead, we reach for the Laplace distribution as follows. So this has the mean at 0 and scale parameter beta here. Or sorry, b. Okay, so here's a graph to illustrate what we mean. On the tails here, we see that the Laplace is bigger than the Gaussian. And in the middle, we see that the Gaussian, is wider in the middle here. And so we expect more values to go in the center, but the extreme values to be not so common at the edges. Laplace is more forgiving to outliers. Now let's run through exactly what we did before, and let's see when we plug this in, what kind of loss do we get? Now you might be able to see it here, but we have this exponent here, and we have this log here. So this term goes to the front, and you probably expect that we have L1 loss, and in fact that's true. Okay, so plugging that in, we have this constant term plus this term here. So dropping this constant term leaves us with this expression here. Now you've seen this before. This is L1 loss. And we know now, we know exactly where this came from. It's not squared error with absolute value instead, because that also seems reasonable. It's the MLE under the specific heavier tail noise assumption. That's why it's more robust to outliers. The model literally expects big deviations to show up sometimes, so it doesn't overpunish them the way the Gaussian assumption would. Okay, so now let's switch to a binary outcome. So yi could be either 0 or 1. So the natural distribution here is a Bernoulli distribution. If y was 1, this term, this exponent is 0, and so this term goes away, and we're just left with the probability of I. Okay, and if yi was 0, then this term goes to 1, and this term crosses out, and we're just left with 1 minus probability of I. Okay, and plugging this expression here, we get the following negative log likelihood. And solving this optimization problem, again, we want to maximize the likelihood. And so since we have this negative out here, we want to minimize the negative log likelihood. And so we can't do any more calculations, of course, but we can take the minimum of the negative log likelihood. And hopefully this expression, well, maybe it looks familiar, but this is called the binary cross-entropy or log loss. Loss of logistic regression and binary classifiers everywhere. Same machine, just a different distribution plugged in. So what if instead of two classes, we have k mutually exclusive categories? We represent yi as a one-hot vector, meaning all zeros except a single one in the position of the true class. And also our model outputs the full probability vector, one entry per class. So here's an example. We have 4 different classes. In this case, the true value for this specific observation, or ith observation, is this observation belongs to class number 2. And so the probability is, of course, the probability that it belongs to class 2. So plugging this value in to this expression here, we have this following expression, which again might be familiar to you. So again, what we want to do is we want to find the parameters which minimizes the negative log likelihood here. So this is the categorical cross-entropy. This is the loss behind basically every multi-class image classifier or any multi-class classifier you've probably heard of. Now, what if we're predicting counts instead? So that's always positive integers, where the variance tends to grow as the count itself grows. So that's the signature of the Poisson distribution. Here, this is the Poisson distribution. Plugging that into our negative log likelihood, we have this expression here, which leaves this expression here as this term is constant, right? yi is from the training data set, so it doesn't affect the optimization problem. So this is, again, you might have seen this before, but this one is less common. This is the Poisson loss. This is the loss you reach for predicting things like website visits or disease case counts or maybe number of purchases, anywhere where the output is a non-negative integer. All right, let's do one more here. So what if we're predicting how long until something happens, which is time, which is always positive and typically skewed, which is, with a lot of short waits and a long tail of rare long ones. So that's the exponential distribution, right? Now plugging that in, we have, and we can't really simplify this anymore, so let's just take the minimum. So we arrive at this loss function, and you might have seen this before. So this shows up constantly in what's called survival analysis and reliability modeling. So that's time until a machine fails, or a time until customer returns, or something like that, related to time until something happens. All right, so that's all the examples I'm going to provide today. So let's take a step back and look at the whole pattern at once. What we started with was we wanted to answer the idea, what is the likelihood of observing our exact data? And of course, that depends on the distribution of our data. And so we can assign different distributions to our data, and we can find these loss function. And how we do that is we ask the simple question, what are the parameters which minimizes the negative log likelihood, which is equivalent to maximizing the likelihood. So if we assume that our data is Gaussian, then we arrive on the L2 loss. If we assume our data comes from the Laplace distribution here, then we find that our loss function is the L1 loss, and so forth. So every loss function you've ever used in machine learning is underneath a hidden claim about how your noise behaves. Pick the wrong distribution and you're not just using a slightly different lens, you're making the wrong statistical assumption about your data. Alrighty, so hopefully that was pretty cool. It gave us the why underneath everything kind of we built across the last 4 weeks. It explained why squared error loss was the right target back in week 23. It also explained why residual sum of squares, or RSS, minimization from week 22 was never arbitrary. It's the Gaussian MLE. And it, directly picked up week 24's crystal dimensionality problem and handed us a general fix for that, which was simply to impose some additional structure, in the statistical form of our joint distribution. And then, almost as a bonus, it handed us a single framework, noise assumption in and loss function out. That basically explains where every single loss function in machine learning actually comes from. So as you can probably tell, this was probably my most favorite week actually so far. So with that, I'll see you next week.